Good afternoon, everybody, and for the audience in the meeting room and for the audience joining us online. I'm Da-Ping Chu, I'm Director of CAPE. Today, we are very pleased to have the pleasure to invite Dr. Yunqing who is the Deputy General Manager and the Chief Engineer of Times Electric UK, to give a talk on his work. Dr. Hu graduated from Hunan Normal University School of Physics and Information in June 2006, with a bachelor degree in Electronic Information Science and Technology. Later, in March 2013, he received a Ph.D. in Control Science and Engineering from Zhejiang University. From April 2013 to April 2014, he worked in CRRC Zhuzhou Institute Co. Limited. And from 2014, in April to May 2017, he worked in the company's Rail Transit Technology Center. Later, from June 2017 to February 2021, he successfully served as the head of the Intelligent Control Technology Department, Deputy Director, Director of Fundamentals and the Platform R&D Center of Zhuzhou Electrical Technology and Material Engineering Academy. Dr. Hu has been appointed as the Deputy General Manager and Chief Engineer of the company since April this year. The title of his talk today is Development of Intelligent Power Control Units for Next-Generation High-Speed EMU Traction System. Dr. Hu, please.
Hello, can you hear me?
Yes, we can.
Yes.
Okay. Hello, everyone. It is nice to meet you all. I have been to CAPE 2 times, and I hope I have a chance in the future and can again. I'm Yunqing from Zhuzhou CRRC Times Electric Limited. Today, I welcome you to the interesting field of railway technology today. Our mission has been to drive innovation in the next generation of railway technology, a fundamental pillar of modern transportation that has continuously evolved, reshaping our travel experience, trade networks, and interpersonal connections. Confronting the challenges posed by our environment, the railway industry has taken significant steps towards sustainability. We are dedicated to creating eco-friendly mobility solutions, paving the way for a greener future. Our systems are infused with energy-efficient technologies, dramatically reducing the carbon footprint of railway transportation. At Zhuzhou CRRC Times Electric, we persistently push the boundaries of innovation. We are focused on developing cutting-edge chips, that means semiconductors, sensors, and automation that have revolutionized the industry, resulting in the creation of our groundbreaking intelligent power converter unit, which means intelligent PCU, a first of its kind next generation technology. This innovation significantly enhances both efficiency and safety standards. Through this presentation, I am glad to guide you through the dynamic field of railway technology at Zhuzhou CRRC Times Electric. We are committed to crafting engineering marvels that offer efficient, reliable, and safer modes of mobility. So I hope you can join us, some students join us, and we can embark on this exciting journey redefining the future of transportation together. My presentation today includes two parts, which are a brief of introduction of Thai Electric and a cutting-edge technology we recently developed. Firstly, I would like to present to you a great company I have known for years. That is my company. Established in September 2005, Zhuzhou CRRC Times Electric is a subsidiary and originating from CRRC Zhuzhou Institute, which was founded in 1959. Zhuzhou TEC is engaged in rail transit, renewable energy, power electronics devices, EV drives, industrial electrical equipment, and marine engineering equipment, which trade twice in over 20 countries. It enhances China's high-speed rail reputation globally and makes it a gold business card of Chinese high-speed railway. The company possesses self-developed core technologies and extensive application capabilities of large-scale application. Here are some basic facts about TEC. Our revenue in 2022 is 18 billion yuan, and the net profit of the year is more than 2 billion yuan. We have more than 8,000 employees, with R&D engineering accounting for 52%. We are a company listed in Shanghai and Hong Kong. We have more than 75 subsidiaries and branches across the world, and we have 3 overseas R&D centers. Here is our organizational structure. It's complex. I will not go deep into it. Zhuzhou TEC created a child-shaped in Chinese career development system and diverse development channels so as to support enterprise development. More than 50% of our employees held a bachelor's degree or higher degree. And we have 6 national level technology innovation platforms and 2 postdoctoral workstations. And TEC has established R&D collaboration with more than 20 global universities, including Cambridge University, Birmingham University, and Warwick University in the UK. And TEC owns a modern industrial manufacturing base over 400,000 square meters. It has China's sole 8-inch IGBT chip production facility. It operates extensive modern large-scale manufacturing base and more than 20 advanced production lines across various cities in China and abroad. And we have built an electric traction system lab, an EMC lab, climate environment lab, wireless information lab, a converter technology comprehensive lab, a network product consistency lab, and a mechanical and environmental lab. With all these laboratories, we are able to carry out almost all the experiments and tests to verify products or technologies. Emphasizing both technology and market, TEC has developed 6 industrial sectors that they are rail transportation, renewable energy, power electronics devices, new energy vehicles, industrial electrical engineering and marine engineering, and gradually build a complete technology chain and industrial chain from chips to system and to full installation. After years of accumulation, we have mastered 10 core technologies. They are electrical system engineering technology, converter technology, train control and diagnosis technology, construction machinery technology, power semiconductor technology, communication signal technology, data and intelligent application technology, traction power supply technology, inspection and testing technology, and subsea robotics technology. Now, I would like to introduce you one of the cutting-edge technologies we have developed in recent years, which is the intelligent PCU for China's next generation of high-speed trains. This part of presentation would include 4 sectors. Their overview, key technologies for PCU, traction device for the next generation high-speed train, and perspective. Overview. People can use electricity to do 2 kinds of work. The first is to use electricity to do information processing. The other one is to do energy processing. Both work requires the use of specific devices. We are familiar with the Intel chip, which is used for information processing devices. And today, we're concerned about the device used for electrical energy conversion, that is, power semiconductor device. Power semiconductor devices are widely used in power system, rail transit, electric vehicles, new energy power generation, industrial transmission, and other scenarios, playing a huge role. Power semiconductor devices have experienced 3 generations of development, which has promoted rapid progress in industries such as rail transit. When talking about the operating conditions, and device requirements of rail transport equipment, what comes to our mind are usually high speed, heavy load, and long range, large fluctuations in ambient temperature and humidity, intense vibration and impact. Therefore, the requirements of easy shutdown, full control, high efficiency, high power density, and high reliability for power semiconductors are proposed. There is a saying in the rail transit industry: a generation of power semiconductors devices determines a generation of traction system, and a generation of traction system determines a generation of trains. Similarly, in areas such as power systems and electric vehicles, device advances have also promoted rapid industry development. China's high-speed train development has gone through 4 stages. The first stage is the self-exploration and technology accumulation stage. And the representative trains of this stage is the China Star train, which has a traction power of 9,600 kilowatts and a maximum speed of 321 km/h. The second stage is the technology introduction and absorption stage. And the representative train of this stage is the harmonic train, among which the maximum power is 8,800 kilowatts, and the maximum speed is 300 kilometers per hour. The third stage is the re-innovation period based on previous introduction and digestion. The representative train of this stage is CRRC 380, which has a traction power of 9,600 kilowatts and a maximum speed of 300 kilometers per hour. The fourth stage is the comprehensive independent innovation stage in China. And the representative train of this stage is the Fuxing train, which has a traction power of 10,000 kilowatts and a maximum speed of 350 kilometers per hour. At present, China's high-speed train research and development and manufacturing level ranks among the top in the world. The continuous development of high-speed trains is driving power devices to advance in areas such as chip technology, packaging, and intelligence. The next generation high-speed train requires enhanced safety, improved environmental friendliness, enhanced energy efficiency, advanced intelligence, great autonomy, enhanced sustainability, system optimization, enhanced speed, and so on. So, a high power efficient inverter with characteristics like high voltage and power, higher reliability, higher efficiency, higher safety, higher power density, and intelligence is required. The advantages of the intelligent power converter unit are high integration, intelligence, high power density, and high efficiency. In this section, I would like to introduce key technologies used in the intelligent PCU. We adopt special packaging materials, low inductance interconnections, chip technologies, high voltage insulation technologies, sensing and diagnosis technology, low thermal resistance technology, active drive control, and PHM technology. All these advanced technologies made it so special. With the development of new chip structure technology, the devices with lower losses and higher current density was made possible. Refinement of cell size, metal size, chip thickness, trench depth, and PN junction depth, and so on, was then achieved. Enhanced emitter carrier storage effects has increased carrier concentration and significantly reduced the voltage drop. Reduction in channel resistance and JFET region spreading resistance decreased chip losses. However, we are still facing challenges such as product parameter uniformity, process platform limited processing accuracy. We developed reverse conducting IGBT by integrating IGBT and fast recovery field, which is FRD, in one chip. Optimized chip areas shared by IGBT and FRD significantly reduced thermal resistance and improving heat dissipation balance, reduced overall chip area, minimize device, and achieving higher current density. Challenges for this technology are appropriate trade-off between IGBT and FRD parameters, increased complexity in design and manufacturing processes. With the improvement in cell refinement, the devices with reduced loss, increased switching frequency, and power density was achieved. A typical solution, embedded emitter change technology, was used here. Method-wise was reduced to 0.6 micrometer, a reduction of over 80%, and the win CE on minus E off trade-off relationship was improved by over 20%, achieving a chip current density of 300 ampere per square centimeter, and a 30% increase. By integrating IGBT and FRD on one chip, a reverse conductive IGBT device with reduced chip area and improved power density is realized. When using the reverse IGBT devices, the thermal resistance of IGBT and FRD are reduced by 30% and 60% respectively, and the equivalent current density reaches 350 ampere per square centimeter. The performance of FRD has been greatly improved, especially in special conditions. Temperature rise is greatly reduced. The change of junction temperature in the switching progress is reduced, and the long-term reliability of the device is improved. We also implemented advanced thermal management technology to decrease the package's thermal resistance, thereby boosting the device's power density. And we developed highly reliable interconnecting technology and manufacturing process to enhance the long-term reliability of the device. We minimized parasitic parameters and balanced them between chips to unlock the device's ultimate potential. We are dedicated to efficient thermal management technologies. As the power device was integrated with the heatsink, the chips would be cooled directly without base plate, which contributed to more 16% reduction of thermal resistance. We implemented silver sintering technology, which would enhance the lifespan and reduce the thermal resistance by at least 10%. Such innovative packaging structure and welding technology leads to reduction of thermal resistance and enhancement of heat dissipation efficiency improvement. By using ultrasonic welding technology to bond power terminals, with the energy delivered by high frequency acoustic wave, cluster phase penetration and interconnection were realized at the interface, which could improve the passive thermal cycling lifetime by more than 2 times. And by using pressureless, low temperature or low temperature assisted silver sintering, uniform and dense interconnection layer can be formed at the interface, which could improve the power cycling lifetime by more than 10 times. And we use copper interconnecting technology by employing super wire or ribbon bonding. The current carrying capacity and chip temperature distribution would be improved, leading to a power cycling lifetime improvement of over 10 times compared to aluminum wire bonding. Internal layout optimization was also conducted. We optimized the power loop layout to bring down the parasitic parameters between different chips, which could reduce the dynamic current imbalance from 28% to 4%. We optimized the control loop by improving the consistency of switching characteristics for paralleling multiple chips, which enhanced the performance of chip under extreme operating conditions. We reduced the strain inductance of the module by utilizing the mutual coupling effect, which leads to a reduction of the turn-off voltage spikes and extend the safe operating area. As for the intelligent technologies in the PCU, for example, self-sensing technology, we integrated high-precision online monitoring of chip temperature and current, which paved the way for improving the reliability of devices. And we developed a diagnostic system based on operational information from internal and external sensors combined with fault logging. We brought out active thermal control by using frequency control and dynamic current limiting to reduce junction temperature and its swing. With the PHM technique, we estimated the lifetime and health status of devices based on their online condition monitoring parameters and performance degradation patterns. Self-perception is an important part of the intelligent PCU. We used the chip-integrated current sensors, which had a response time for overcurrent and short circuit protection less than 2 microseconds, which is even faster than traditional methods, and thus enhanced the safety of the devices. Meanwhile, high voltage isolation, sensing, signal extraction, and current ratio posed us huge challenges. Chip-integrated temperature sensors had a much faster response time than NTC, and the temperature difference from junction temperature was less than 8 centigrade, which would be favorable for improving the current output capacity of the chips. At the same time, crosstalk of bulk, silicon diode, and temperature coefficient of sensor pose technical challenges on us. Self-diagnosis was also an indispensable part of PCU. We adopt condition-based diagnosis based on online extraction and intelligent algorithm. We implemented real-time diagnosis of the PCU operating status for rapid identification and localization of faults based on online extraction of dynamic parameters using chip self-sensing and external sampling, as well as the failure mode data and degradation loss. Online extraction and real-time diagnosis could ensure more reliable operation of PCU-based systems. As for the thermal management part, we managed to attain the active temperature control. As the fluctuation of junction temperature of chips was low frequency and high amplitude, we found out that the lifespan of chips decreased to 1/10 when junction temperature fluctuation increased by 10 K. Then we researched on the active temperature control technology based on two aspects of heat loss control of PCU devices and heat sink design. In the end, we reduced the maximum temperature fluctuation of heat sink by about 18 K and decreased the junction temperature fluctuation by 21 K, which could improve the lifespan of PCU significantly. Active temperature control technology significantly reduced the junction temperature fluctuation of PCU chips and enhanced the lifespan. We assessed the health status based on IGBT status, a state parameter monitoring. We extracted the PCU state parameter changes with performance degradation and established the degradation model by using real-time collection of PCU operational state parameters as inputs to the assessment model and output the results of the model to assess the health status. We also applied our advanced PHM technologies in this device, including online state parameter monitoring circuit, device junction temperature estimation, parameter estimation and data normalization processing, device fault warning and health status assessment algorithms, device remaining life prediction model, device failure warning and remaining life assessment results, and maintenance recommendations. With these PHM technologies, we can collect real-time PCU operating conditions, extract health factors, reflecting degradation patterns, as well as health status assessment. Okay, in this part, I'm going to introduce how would PCU make a difference to the next generation high-speed train in China. At present, China is developing a new generation of high-speed trains. Its goals include commercial operating speed of 400 km/h. Axle load is reduced to 14.5 tons. Energy consumption remains the same as the current speed of 350 km/h train. The next generation high-speed train aims to achieve higher speed, improved safety, enhanced environmental friendliness, better efficiency, advanced intelligence, greater autonomy, improved sustainability, and overall system optimization. The traction inverter unit is required to deliver a power output of no less than 4 × 3 megawatts, with an efficiency of no less than 97% and a weight not exceeding 3,250 kilograms. PCU stacking solution significantly shortens maintenance time, reduce labor, and lower spare parts costs. The weight of module assembly can be reduced from 50 kilograms to 5 kilograms with the use of PCU compared to conventional converters. Maintenance time reduced from 30 minutes to 5 minutes. Spares are measured in devices instead of components. PCU-based traction converters are more powerful, smaller, and lighter, with the same converter topology and main circuit compared to the CR400AF converter. The PCU-based converter offers a 20% increase in power rating and a 16.5% reduction in size and an 11% reduction in weight. System solutions based on PCU in the entire train traction system power density and efficiency metrics achieve world-leading levels. Total power is 12,000 kilowatts. Total efficiency is 90.8%. Total power density is 339 kilowatts per ton. This page shows some PCU application examples. The 350 km/h double-decker high-speed train has successfully completed a full load loop operation compared to 350 km/h standard train. The PCU-based train offers a 7% reduction in volume and a 30% reduction in weight. The next generation 400 km/h high-speed train has successfully completed prototype line testing. PCU-based trains are 26% smaller and 27% lighter than standard train at 350 km/h. The China's next generation high power electric locomotive is in process of prototype development, which will be 20% smaller and about 11% lighter. The CR450 train achieved a remarkable speed of 891 km/h during open track crossing and 814 km/h in tunnel crossing, setting a new world record for high-speed rail crossings. Okay, perspective. Breakthrough in device technology are based on new materials, new structure, new packaging technology, and intelligence. For a virtuous cycle in which device technology promotes progress in application technology, and application technology drives breakthroughs in device technology. The feasibility of combining PCU technology with silicon carbide and high voltage super junction chips will be actively evaluated in the future. As an autonomous universal power platform, PCU embrace new materials and new structure and breaks the limits of the silicon-based devices. In the future, we will continue to optimize the packaging by means of multi-physics coupling and multi-objective optimization. Next stage of research, development, and application of the next generation power devices will be integrating control, intelligence, and safety technologies, achieving multi-physics optimization and flexible customization. focusing on high efficiency, density, lightweight, and intelligence, more efforts will be driving advancements in rail transport, renewable energy, power system, and industrial transmission for high quality development. That's all for my today's presentation, and thank you for listening. Thank you.
Thank you.
Thank you very much, Dr. Hu, for this exciting talk, and it's a comprehensive overview. And now I think the talk is open to questions. And people online, if you wanted to ask questions, you can send it through the chat. Anybody has any questions? Dr. Hu, I think I have a question about, you mentioned the new materials, but you also touched a little bit on the packaging technology. Can you tell us a bit more the importance of the packaging technology and the direction for the power electronics?
Okay, and I have my colleagues online, and they are more professional than me. So I want to then ask you a question: the packaging technique and their development directions. 我们讲一下这个未来在封装这一块的技术的这个内容和发展方向。朱博士这边您讲一下吧。
好，我来讲了。Hello everyone. For the packaging technology, which is indeed very important, packaging materials protect our silicon devices, silicon chips, and also using the packaging technology to bring the current, the power out of the power semiconductor chips. So for the advanced packaging technology, just like Dr. Hu mentioned, I think there are three aspects. Like the first one is advanced interconnections, like for example, ultrasonic welding compared with conventional soldering technology, which has bring lower thermal and and also bring higher reliability of the interconnection interface. For the chip interconnection, we are developing the self-sintering compared with a conventional solder, which brings lower thermal resistant and higher reliability, higher lifetime, like more than 10 times of conventional technology. And also with wire bonding technology, we bring the copper wire bonding or copper ribbon compared with the conventional aluminum wire bonding, which also brings higher lifetime. The second one is the new material for the packaging technology, which is bring higher insulation performance and also bring higher thermal performance. And also for the...
Please continue. Yeah.
Okay. And also for the packaging technology, the third one, which is very important, is thermal management, which is bring the heat dispensation from the silicon chip So we use different new material to bring the heat of the silicon chip more efficiently, and use silicon and use silver sintering and other technology to lower the thermal resistance to bring a high performance of the silicon devices. That's all. Thank you.
Thank you very much. I think, yeah, it's like you have an all-round of the packaging technologies, not only just the next generation semiconductor material, but the packaging, I think, is also, yeah, as I mentioned, very important here.
Yes.
Any other questions? Yeah, here.
I have a question in terms of the choice of power devices in the next generation of PCU. Through your lecture, I find that CRRC is still refining your IGBT technology, and will CRRC consider using silicon carbide power devices for the next generation of PCU? And is that a viable choice? I mean, in terms of the cost and reliability, to use silicon carbide devices, which may be more efficient in their next generation PCU. Yeah, thank you. That's my question.
Thanks for your question. Yes, at present we are developing silicon carbide device in CRRC. Actually, we know that silicon carbide device is very it is low loss, so that it can enable high efficient and high output current. About the reliability, actually, most of the silicon carbide devices sold in the market, the technology problem has already been solved, especially on the HTRB and HTB problems. So at present, I think the silicon carbide power device technology is already mature, and it is ready to be used in the powertrain. Actually, some of the power device, silicon carbide power devices, has already been used in CRRC in the train. Actually, and in the future, at present we have IGBT PCU, a silicon IGBT PCU, and in the future we can develop silicon carbide power device based PCU devices. So I don't know whether I answered your question. If you have any other questions, I can answer.
Yeah, that's answered my question. Thank you very much. Yeah.
Thank you. Any other questions?
Okay, and I want to add an explanation. We, of course, we have silicon carbide products for the traction system, and the material silicon carbide has its advantages such as high frequency and lower loss. It's good. However, it's very dear currently. So we hope in the future it could be cheaper as IGBT. At present, we think IGBT based traction is enough for the next generation of Chinese high-speed train. Thank you.
Thank you.
Hi, Dr. Hu, and thank you for your presentation. It's quite interesting, but because I'm not within your area, so may I propose a maybe silly question? Like you mentioned, like you are proposed to develop the next generation for the high-speed train. So may I know like what's the design lifetime of this kind of the train? And you mentioned like, for instance, the speed will be increased, of course. So during the design, will you also replace the current infrastructures, for instance, the railways? Like, are they doable to for the new design of the new trains? And will you consider like to change them to the more, for instance, more resistant materials for the high speed of the train? Yes, thank you.
The question is about next generation high-speed train. Yeah.
Yeah.
I'm sorry. Would you please repeat your question slowly?
Yeah. Sorry. So I'm wondering, like, as you said, you are planning to develop the next generation high-speed train. So during that time, will you also replace the current infrastructures? For instance, the railways in China. Like, according to my understanding, I know like the railway has covered a large area of the China, which can be millions of the kilometers long. So to fit in the next generation trains, will you choose to change them to the more resistant and durable materials for the railways? Thank you.
铁路基建需不需要也要同步的这个优化？
会用新的PCU。
对。
株洲这边这个听清他的问题吗？我没有听得太多。
Okay. So, let me answer this question.
他想问一下，现在的
这个基础设施，
中国的这个铁路上面的这些基础设施、铁轨啊这些设施，如果进一步提速的话，作为下一代的这个高铁，现在的这些铁轨是不是需要更换？其他的这个设施是不是需要更换？还是可以满足下面的要求需要？
因为这一块我们主要是这个从事轨道交通这个装备的这一块的啊，就是铁路基建设施啊，按照理论上讲是需要做进一步的提升的，因为速度提高了以后啊，提出了更高的一些要求。
Okay, so the answer is the infrastructure might need to be upgraded for the next generation train, but currently I think there are probably still rooms for incremental improvement. Yeah.
Thank you so much.
Hi. Any other
Okay,
questions? Yeah, sure. Go ahead. Yeah, Dr. Hu, please.
Okay. In CRRC, we have almost about 50 companies. Some companies make trains. Some companies make equipment, such as us. So it's a very big question to say next generation. But I think yes, the infrastructure and the trains should change themselves to suit higher speed. In my opinion, I think the current infrastructure can satisfy in some region about 600 km/h. But if you continuously increase the speed, I think the infrastructure cannot satisfy. Thank you.
Thank you. Thank you. That's very helpful. Any other questions? I don't see online. So I think it's quite a long time. Let's thank Dr. Hu and his colleague again.
Thank you. It's my pleasure.
Very much. I think the lecture is closed now. Thank you. Thank you very much.
Thank you.